In an earlier video, I mentioned that the final obstacle preventing the quantification of understanding was my inability to meaningfully rank and extend the levels of measurement. Just recently, however, I discovered the missing piece to this puzzle and can now actually quantify understanding. My discovery started after I learned about a formula developed by Claude Shannon. The rightmost piece of his equation actually can quantify the amount of information received by learning the outcome of an event. This piece's only input is the probability of that specific event happening. For example, the amount of information received by hearing the statements, "The sun rose from the east today," and "There was a supernova explosion in the Milky Way today," are 0 bits and 49.83 bits, respectively. I realized Shannon's formula provided me with an attribute I could use to meaningfully rank and extend the levels of measurement. This is the amount of information contained within a certain scale. In order to find this amount of information, I needed to calculate the probability that a person could randomly guess the correct scale on the first try. For example, what is the probability that an individual could randomly guess this particular ordinal scale, knowing only that it must contain the minerals talc, gypsum, calcite, and fluorite? To make this problem more specific, I considered placing the objects on several number lines, which represent the mineral's hardness. The consistent diagrams on the left accurately represent the particular ordinal scale, while those on the right do not. Recall that on an ordinal scale, only the order of the objects is important, not the numerical positions or the distance in between objects. By creating these diagrams, my question then becomes, what is the probability of a person randomly guessing one of a particular scale's consistent diagrams if they are given only a number line and the objects? At first, this question was seemingly difficult to solve. I realized that I would need to consider placing a cup on every single real number, but I did not know how to do so, as the number line is continuous, not discrete. After some thinking, however, I figured out how to do it. Consider a line that spirals outwards from 0 and intersects integers along the way. Here is an example of an 11 spiral, which is labeled as such because it intersects 11 of the centermost integers. The orange circles, which lie on the intersections, are called cups because they each are the top view of a cup. If the spiral continues intersecting integers forever, it becomes an infinity spiral, which is a spiral that intersects all the integers. Now consider stretching the number line intersecting an infinity spiral in a way that preserves the ratio of the distances. If the number line is stretched indefinitely, a cup will eventually lie on every single real number. This thought experiment provided me with the intuition necessary to develop the probability formulas for each scale type. I will begin by developing a formula to calculate a ratio scale's probability. Consider a ratio scale of 2 75 kilogram objects, 3 100 kilogram objects, and 2 125 kilogram objects. In a ratio scale, there is only one consistent diagram, which is pictured here on screen. The probability of a person randomly generating this single consistent diagram is the product of the probabilities of placing each object into the correct real number cup. This algorithm can be succinctly expressed using the formula below. The line R line symbol represents the total number of real numbers, and the O represents the total number of objects. The formula for calculating an interval scale's probability can be derived using the ratio scale's probability formula. Consider an interval scale of 2 SAT scores 200 points less than 3 SAT scores. The number of consistent diagrams possible is equal to the total number of real numbers, because a new one can be made by simply transferring the objects to an adjacent cup. The formula for calculating an interval scale's probability is the product of the ratio scale's probability formula and the total number of real numbers. This is because the probability of each consistent diagram can be calculated using the ratio scale's probability formula, and because there are as many consistent diagrams as there are real numbers. The intuition behind the ordinal scale's probability formula is hard to explain simply, so I will just show its application. Consider an ordinal scale of 3 sour, 2 medium, and 2 sweet apples. On screen, I have shown some of the scale's consistent diagrams. The ordinal scale's probability formula, unlike those previously shown, have one extra input. F is the total number of filled cups in each consistent diagram, which is, in this case, 3. The C denotes the usage of the combination formula. I will also not explain the intuition behind the nominal scale's probability formula. On screen, I have shown the consistent diagrams of a nominal scale made up of 3 verbs, 2 nouns, and 2 adjectives. The only difference between the nominal and ordinal scale's probability formula is that instead of using the combination formula, the nominal scale version uses the permutation formula. Because the outputs of these 4 formulas are probabilities, they can be inputted into the part of Shannon's formula which quantifies information. This combination allows the quantification of the amount of information stored within any particular nominal, ordinal, interval, or ratio scale. I can now more precisely solve the question brought up in the previous video. The change in the man's absolute understanding of the orange box is the number of bits displayed on screen. Notice that the unit of understanding is the same as the unit of information. Because the number of bits is a positive value, the man's absolute understanding of the box has increased. Although I have made great progress in quantifying understanding, there are still some tasks that have not yet been accomplished. For example, I have not created the probability formulas for other levels of measurement, which can be made by selecting a different set of consistent diagrams. Also, I have not yet considered the probability functions of scales with multidimensional consistent diagrams. I will save those endeavors for future videos. Thank you for watching.